Right now, somewhere in the depths of space, there exist galaxies that shouldn't be possible according to everything we understand about cosmic structure. These are galaxies completely devoid of dark matter, the invisible cosmic scaffolding that supposedly holds the universe together and makes galaxy formation possible in the first place. We thought dark matter was as fundamental to galaxies as skeletons are to vertebrates. Yet astronomers have discovered galactic systems thriving without any dark matter whatsoever, like finding perfectly healthy animals with no bones. Here is what makes this discovery so profoundly disturbing. Dark matter is supposed to comprise 85% of all matter in the universe, forming the gravitational framework upon which ordinary matter organizes itself into stars, planets, and galactic structures. For over 50 years, every model of galaxy formation has assumed that dark matter halos provide the essential gravitational wells where ordinary matter can accumulate and ignite into stellar systems. Yet these dark matter-free galaxies exist in apparent violation of cosmic law, spinning peacefully through space as if dark matter never existed. The numbers are staggering when you grasp their implications. A typical galaxy like our Milky Way contains roughly 10 times more dark matter than ordinary matter, with this invisible component extending far beyond the visible galactic disk to create massive gravitational halos spanning hundreds of thousands of light years. But the galaxies we are about to explore, NGC 1052 DF2 and NGC 1052 DF4, show no evidence of dark matter halos despite containing billions of stars, organized into coherent galactic structures that should be impossible without dark matter as gravitational scaffolding. Scientists from Yale University announced in 2018 that they had discovered the first confirmed galaxy completely lacking dark matter, a finding so shocking that it initially met with scientific skepticism and demands for independent verification. Dr. Peter Van Dokkum, who led the discovery team, called it the most important galaxy discovery in decades because it challenges fundamental assumptions about cosmic structure that have guided astrophysics research since the 1970s. Tonight, we're going to explore the most revolutionary discovery in modern cosmology. You're about to learn why galaxies without dark matter represent either the greatest vindication of dark matter theory or its complete overthrow, and why understanding these cosmic anomalies could transform our grasp of gravity, matter, and the fundamental forces that shape reality itself. We'll all journey from the theoretical foundations of dark matter to the cutting-edge observations that have shattered cosmic orthodoxy. But first, consider this mind-bending possibility. If galaxies can exist without dark matter, what does that reveal about the nature of dark matter itself? Is it truly the fundamental cosmic component we believe? Or could these galaxies be revealing that our entire understanding of cosmic structure rests on incorrect foundations? This isn't just about exotic galaxies in distant space. This is about discovering that the universe operates according to principles we haven't yet grasped, where cosmic structures can form through mechanisms that violate everything we think we know about gravitational physics and cosmic evolution. What appears to be cosmic impossibility might reveal cosmic possibility beyond our current theoretical frameworks. The ancient philosophers wondered whether reality consists of what we can see or what remains hidden from view. Modern astronomy has spent decades mapping invisible dark matter throughout cosmic space, only to discover galaxies that seem to prove dark matter is unnecessary for cosmic structure. Tonight, you're going to learn that the universe's greatest mystery isn't what dark matter is. It's why some cosmic structures don't need it at all. By the time we finish this cosmic investigation, you'll understand why dark matter-free galaxies have forced scientists to question century-old assumptions about gravity and cosmic structure. You'll discover how these galactic anomalies could represent cosmic laboratories where alternative physics theories might be operating according to principles that transcend our current understanding of fundamental forces. You'll learn why some physicists now argue that dark matter-free galaxies provide the smoking gun evidence for modified theories of gravity that could eliminate the need for dark matter entirely. And you'll see why understanding these cosmic exceptions might reveal that our universe operates according to gravitational principles far more exotic and beautiful than anything predicted by current physical theories. The implications extend far beyond astrophysics to encompass fundamental questions about the nature of space, time, and gravitational interaction itself. If galaxies can maintain structural integrity without dark matter halos, then either dark matter behaves in ways we don't understand, or gravity operates according to principles we haven't discovered, or cosmic structure formation follows pathways we haven't imagined. Subscribe and hit the thumbs up button if you're ready to have your understanding of cosmic structure completely revolutionized. And here's a question that will challenge everything. If some galaxies can exist without dark matter, could our entire universe be fundamentally different from what we've assumed for the past half-century? Comment your most mind-bending theories below. I'll pin the response that best captures the cosmic mystery we're about to unravel. The galaxies that shouldn't exist according to dark matter theory are about to teach us that cosmic reality might be far stranger, far more flexible, and far more mysterious than our most advanced theories have ever suggested. We're going to discover that sometimes the most important scientific discoveries come not from finding what we expect, but from finding what shouldn't be possible at all. The universe that seemed to require dark matter to hold itself together is revealing cosmic structures that thrive without it, suggesting that cosmic reality operates according to principles that make the impossible inevitable and the unprecedented perfectly natural. Now, let's begin our journey into the heart of this cosmic contradiction. Chapter 1. Dark Matter Foundation. To understand why galaxies without dark matter represent such a profound cosmic mystery, you first need to grasp how completely dark matter has dominated our understanding of cosmic structure for over 50 years. Dark matter isn't just a minor component of cosmic models. It represents the fundamental scaffolding upon which all modern theories of galaxy formation, cosmic evolution, and universal structure have been built. Discovering galaxies that lack dark matter is like finding buildings that stand perfectly upright despite having no foundations. The dark matter story begins in 1933, when Swiss astronomer Fritz Zwicky was studying the motion of galaxies within the Coma cluster, a massive collection of galaxies bound together by gravity. Using the virial theorem, a fundamental principle relating orbital velocities to gravitational mass, Zwicky calculated that the galaxies were moving far too quickly to remain gravitationally bound by the visible matter alone. The cluster should have dispersed billions of years ago unless it contained much more mass than telescopes could detect. Zwicky coined the term Dunkel Materie, dark matter, to describe this missing mass. But his discovery remained largely ignored for decades until Vera Rubin's revolutionary observations in the 1970s provided even more compelling evidence. Dr. Rubin studied rotation curves of individual spiral galaxies, measuring how quickly stars orbit around galactic centers at different distances from the core. According to Newtonian physics, stars in outer galactic regions should orbit more slowly than inner stars, just as outer planets in our solar system orbit the Sun more slowly than inner planets. Instead, Rubin found that galactic rotation curves remain flat across their entire observable extent. Outer stars orbit just as quickly as inner stars, violating everything astronomers expected from visible matter distribution. The only way to explain these flat rotation curves was to propose that galaxies are embedded within massive halos of invisible matter, extending far beyond their visible boundaries, providing additional gravitational attraction that accelerates outer stellar orbits. The Hubble Space Telescope and subsequent surveys have revealed that this dark matter component dominates cosmic structure throughout the observable universe. Galaxy clusters, individual galaxies, and even dwarf galactic systems all exhibit gravitational evidence for dark matter halos containing 5 to 10 times more mass than all visible stars, gas, and dust combined. Dark matter became the cosmic majority, with ordinary matter relegated to a minor constituent riding within dark matter's gravitational framework. Computer simulations of cosmic structure formation, such as the Millennium Simulation and the Illustristing project, demonstrated that dark matter halos provide the essential gravitational wells where ordinary matter can accumulate and cool sufficiently to trigger star formation. Without dark matter's gravitational scaffolding, the universe would remain a smooth, featureless expanse of hydrogen and helium gas, never developing the density contractions necessary for stellar ignition and galactic assembly. The lambda-C-DM model, lambda cold dark matter, became the standard model of cosmology, successfully explaining cosmic microwave background observations, large-scale structure formation, and galaxy evolution across cosmic time. This model assumes that dark matter consists of exotic particles that interact gravitationally, but not electromagnetically, making them invisible to telescopes while providing the gravitational framework for all cosmic structure. Dr. Carlos Frank's theoretical work on dark matter particle physics proposed that these mysterious particles emerged from the Big Bang with specific properties that enabled them to clump together into halos before ordinary matter began forming stars. Cold dark matter, meaning particles with relatively low velocities, could form gravitational concentrations across a wide range of scales, from dwarf galaxy halos to massive galaxy cluster halos spanning millions of light years. The European Southern Observatory's Very Large Telescope has observed gravitational lensing effects that provide direct evidence for dark matter as gravitational influence. When light from distant galaxies passes through dark matter concentrations, the gravity bends light paths and distorts background galaxy images. By analyzing these distortions, astronomers can map dark matter distributions invisible to direct observation, confirming that dark matter halos surround every observed galactic system. NASA's Chandra X-ray Observatory revealed additional evidence through observations of galaxy cluster collisions, where dark matter and ordinary matter behave differently during gravitational encounters. The famous bullet cluster collision shows ordinary matter interacting and heating during collision, while dark matter components pass through each other without significant interaction, exactly as predicted by dark matter particle theories. But the dark matter foundation extends beyond individual galaxies to encompass cosmic structure across the entire observable universe. The cosmic web, the largest scale structure pattern spanning billions of light years, emerges naturally from dark matter halo formation and merger processes operating across cosmic time. Galaxy filaments, galaxy clusters, and cosmic voids all reflect underlying dark matter architecture established during the universe's early evolution. The Planck satellite's measurements of cosmic microwave background fluctuations reveal that dark matter comprises approximately 26.8% of cosmic energy density, compared to only 4.9% for ordinary matter and 68.3% for dark energy. This cosmic accounting makes dark matter 5 times more abundant than the ordinary matter that forms stars, planets, and biological systems, establishing dark matter as the dominant gravitational influence in cosmic structure formation. Ground-based surveys like the Dark Energy Survey and the upcoming Large Synoptic Survey Telescope continue mapping dark matter distributions across cosmic space and cosmic time, revealing how dark matter halos evolve through cosmic history while maintaining their role as gravitational foundations for galactic ecosystems. These observations consistently confirm dark matter's fundamental importance for cosmic structure across all observable scales. The particle physics community has invested billions of dollars in experiments designed to detect dark matter particles directly through underground laboratories, space-based detectors, and particle accelerator experiments. Projects like the Large Underground Xenon Experiment and the Alpha Magnetic Spectrometer search for evidence of dark matter-particle interactions or decay products that would confirm dark matter's particle nature. Theoretical physics has developed sophisticated models of dark matter particle candidates, including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos, each with specific predictions about dark matter behavior that could be tested through astronomical observations and laboratory experiments. These models provide detailed frameworks for understanding how dark matter particles formed during the Big Bang and evolved to create today's cosmic structure. Consider the profound implications of dark matter's foundational role in cosmic structure. Every galaxy, every star, every planet, and every biological system exists because dark matter halos provided the gravitational environments where ordinary matter could accumulate and evolve into complex cosmic ecosystems. The calcium in your bones, the iron in your blood, the oxygen you breathe, all exist because dark matter created the cosmic conditions necessary for stellar nucleosynthesis and planetary formation. Your existence depends directly on dark matter's gravitational influence across billions of years of cosmic evolution. The Milky Way galaxy that contains our solar system formed within a dark matter halo that continues regulating galactic structure and stellar formation processes. Without dark matter, cosmic structure formation would never have progressed beyond smooth hydrogen and helium gas expanding with cosmic space. Now we were going to explore how this fundamental cosmic foundation faces its greatest challenge from the recent discovery of galaxies that appear to violate dark matter theory by existing without any dark matter whatsoever, forcing scientists to question whether dark matter is truly as fundamental as 50 years of research has suggested. Chapter 2. The Impossible Discovery. In March 2018, the astronomical community was shaken by an announcement that challenged 50 years of cosmic orthodoxy. Yale University's Peter Van Dokkum and his team had discovered a galaxy that appeared to contain no dark matter whatsoever. NGC 1052DF2, a diffuse galaxy located approximately 65 million light-years away, exhibited stellar motions indicating that its visible matter accounted for essentially all its gravitational mass, a finding that seemed to violate fundamental assumptions about galaxy formation and cosmic structure. The discovery wasn't accidental, but emerged from systematic surveys designed to study ultra-diffuse galaxies, faint, extended stellar systems that had only recently become detectable with advanced telescopes. Dr. Van Dokkum's team was using the Dragonfly telephoto array, a specialized instrument consisting of multiple telephoto lenses designed to detect extremely low surface brightness objects that conventional telescopes miss due to scattered light contamination. NGC 1052 DF2 immediately stood out as anomalous when initial observations revealed a galaxy containing roughly 200 million stars spread across a region 15,000 light-years in diameter, similar to our galaxy stellar disk, but with far lower stellar density. What made this galaxy extraordinary wasn't its diffuse structure, but the behavior of globular clusters, dense stellar associations that orbit within the galaxy's gravitational field, like cosmic lighthouses marking gravitational contours. The team measured velocities of 10 globular clusters orbiting within NGC 1052 DF2 using the Keck Observatory's precision spectrographs, expecting to find orbital speeds indicating substantial dark matter halos as observed in every other galaxy. Instead, they discovered the globular clusters were moving at speeds consistent with the gravitational influence of visible matter alone, suggesting the galaxy contained essentially no dark matter component. This finding represented a direct contradiction to lambda-CDM cosmological models, which predict that all galaxies should form within dark matter halos containing 5 to 10 times more mass than visible stellar components. NGC 1052 DF2's globular clusters were orbiting at approximately 30 kilometers per second, far too slowly to indicate significant dark matter presence. If dark matter halos were present, globular cluster velocities should exceed 100 kilometers per second to maintain stable orbits within the galaxy's gravitational field. Dr. Shani Danieli, a key member of Van Dokkum's discovery team, calculated that NGC 1052 DF2's total mass approximately equals its stellar mass, implying a dark matter fraction near 0% compared to the 80 to 90% dark matter fraction typical of most galactic systems. This galaxy appeared to consist almost entirely of ordinary matter, organized into stellar systems without any invisible gravitational scaffolding. The scientific response was immediate and intense, with numerous research groups demanding independent verification of such an extraordinary claim. The discovery challenged fundamental assumptions about galaxy formation that had guided astrophysics research for decades, requiring exceptional evidence to overcome decades of consistent dark matter observations throughout cosmic structure. Independent observations using the Hubble Space Telescope confirmed the galaxy's basic properties, its stellar content, spatial distribution, and distance measurement, while additional spectroscopic studies verified the anomalously low velocities of globular clusters orbiting within the galactic system. Multiple observational teams reached similar conclusions. NGC 1052 DF2 exhibited no detectable evidence for dark matter halos despite containing organized stellar populations spanning thousands of light years. But the discovery became even more remarkable in 2019 when the same research team announced NGC 1052 DF4, a second dark matter-free galaxy located in the same cosmic region. This second galaxy exhibited similar properties: diffuse stellar distribution, low-velocity globular clusters, and total mass consistent with visible matter alone. The existence of two dark matter-free galaxies in proximity suggested systematic processes rather than unique cosmic accidents. The implications of these discoveries extend far beyond cataloging unusual galactic systems. If galaxies can form and maintain structural integrity without dark matter halos, then either our understanding of dark matter is fundamentally incomplete, or galaxy formation processes are far more diverse and complex than current theoretical frameworks suggest. Dr. Michelle Capillari from Oxford University pointed out that dark matter-free galaxies could represent natural experiments testing alternative theories of gravity and cosmic structure. Modified Newtonian dynamics, MOND, and other alternative gravity theories had long predicted that cosmic structure might form without requiring dark matter, but lacked clear observational tests. Dark matter-free galaxies potentially provide the crucial observations needed to distinguish between dark matter theories and alternative gravity models. The discovery also raised profound questions about galaxy formation mechanisms. Standard models assume that galaxies form through ordinary matter cooling and condensing within pre-existing dark matter halos established during cosmic structure formation. But dark matter-free galaxies suggest alternative formation pathways where gravitational dynamics, stellar feedback, or environmental processes can create galactic systems without dark matter scaffolding. Theoretical astrophysicist Dr. Abraham Loeb from Harvard University proposed that dark matter-free galaxies might form through tidal stripping processes, where gravitational interactions with massive nearby galaxies gradually remove dark matter halos while leaving stellar components gravitationally bound. This mechanism could explain why both NGC 1052 DF2 and NGC 1052 DF4 exist near NGC 1052, a massive elliptical galaxy that could provide the tidal forces necessary for dark matter removal. But tidal stripping models face challenges explaining how stellar components remain gravitationally bound after dark matter removal. Since dark matter halos typically extend far beyond visible stellar distributions and should be less susceptible to tidal disruption than stellar components. Alternative formation mechanisms involving primordial gas dynamics, stellar feedback, or exotic physics processes remain speculative and require additional theoretical development. The European Space Agency's satellite has begun measuring proper motions and distances for nearby ultra-diffuse galaxies, potentially revealing additional dark matter-free systems that could establish whether these objects represent rare exceptions or previously unrecognized galactic populations. If dark matter-free galaxies prove more common than initially suspected, the implications for cosmological models could be revolutionary. NASA's James Webb Space Telescope will soon provide unprecedented observations of ultra-diffuse galaxies, measuring stellar populations, chemical compositions, and star formation histories that could reveal formation mechanisms responsible for creating galactic systems without dark matter halos. These observations will test whether dark matter-free galaxies formed through known astrophysical processes or require exotic physics beyond current theoretical frameworks. The impossible discovery of dark matter-free galaxies has already forced theoretical physicists to reconsider fundamental assumptions about cosmic structure formation. If dark matter is truly fundamental to cosmic evolution, then dark matter-free galaxies must form through exceptional processes that remove or prevent dark matter accumulation. Alternatively, these galaxies might reveal that cosmic structure can form through gravitational mechanisms that don't require dark matter at all. Consider the philosophical implications of discovering cosmic structures that violate foundational theoretical assumptions. Science progresses through challenging established paradigms with new observations that force theoretical evolution. But dark matter-free galaxies challenge paradigms so fundamental that accepting their implications could require reconstructing cosmological models from first principles. Your understanding of cosmic structure has been built upon dark matter's presumed universality throughout galactic systems. Yet these impossible galaxies suggest that cosmic reality might be far more diverse and mysterious than our most comprehensive theories have suggested. The universe reveals itself capable of creating structures that shouldn't exist according to our best scientific understanding. Now, we're going to explore how scientists are attempting to explain these impossible galaxies through various theoretical mechanisms, and why each proposed explanation reveals new mysteries about the fundamental nature of cosmic structure and gravitational physics. Chapter 3: Formation Mysteries. The existence of galaxies without dark matter has forced astrophysicists to develop entirely new theoretical frameworks for galaxy formation, since every established model assumes that dark matter halos provide the essential gravitational scaffolding for galactic assembly. The challenge isn't simply explaining how these galaxies formed, it's understanding how they could form at all, given everything we know about cosmic structure formation over the past 13.8 billion years of cosmic evolution. The most widely discussed formation mechanism involves tidal stripping, gravitational interactions that could theoretically remove dark matter halos from galaxies while leaving stellar components intact. Dr. Laura Sales from the University of California, Riverside, has developed sophisticated computer simulations showing how massive galaxies can gravitationally strip dark matter from smaller, neighboring systems through repeated close encounters over hundreds of millions of years. These tidal stripping models reveal a complex gravitational dance where dark matter particles, being more weakly bound to galactic centers than stellar components, get preferentially removed during gravitational encounters. As a dark matter-rich galaxy passes near a massive neighbor, tidal forces stretch the dark matter halo while stellar components remain more tightly bound due to their higher central concentration and stronger gravitational cohesion. But tidal stripping faces significant theoretical challenges when applied to observed dark matter-free galaxies. Computer simulations by Dr. Jorge Penarrubia from the University of Edinburgh show that removing 99% of dark matter through tidal interactions typically requires removing 80 to 90% of stellar mass, simultaneously making it difficult to explain galaxies that retain substantial stellar populations while losing essentially all dark matter content. The timing requirements for tidal stripping also present problems when comparing theoretical predictions to observational constraints. NGC 1052-DF2 and NGC 1052-DF4 would need to have experienced precisely calibrated gravitational encounters that remove dark matter without disrupting stellar organization, a scenario requiring exceptional fine-tuning of orbital parameters, encounter velocities, and galaxy masses. Alternative formation mechanisms invoke primordial processes operating during cosmic structure formation itself. Dr. Raphaël Gavazzi from the Institut d'Astrophysique de Paris proposes that dark matter-free galaxies might form from primordial gas clouds that never accumulated significant dark matter during cosmic structure formation, possibly due to feedback from early stellar populations or supermassive black hole activity. These primordial formation models suggest that intense stellar feedback during galaxy formation could heat and expel dark matter from developing galactic systems before it became gravitationally bound. Supernovas, stellar winds, and active galactic nuclei could provide energy inputs sufficient to accelerate dark matter particles beyond escape velocity, while ordinary matter remains trapped within evolving gravitational potentials. Dr. Aaron Romanowski from San Jose State University has investigated whether dark matter-free galaxies could form through failed galaxy scenarios where dark matter halos captured insufficient ordinary matter to trigger substantial star formation. In these models, most dark matter remains distributed in extended halos, while ordinary matter forms compact stellar systems that subsequently separate from their dark matter hosts through dynamical evolution. But failed galaxy models struggle to explain the observed stellar masses and spatial distributions of dark matter-free galaxies, which contain hundreds of millions of stars organized into coherent structures spanning thousands of light years. These stellar systems appear too substantial and well-organized to represent failed galaxy formation processes. The European Southern Observatory, Very Large Telescope, has conducted follow-up observations searching for faint stellar streams or disrupted stellar populations that might indicate violent formation histories consistent with tidal stripping or explosive feedback mechanisms. These observations reveal remarkably smooth stellar distributions without obvious signs of recent disruption, suggesting formation processes that preserved stellar organization while eliminating dark matter. Exotic formation mechanisms involving modified gravity theories present intriguing alternatives to dark matter-based explanations. Modified Newtonian dynamics, MOD theory, developed by Dr. Mordechai Milgram, proposes that gravitational dynamics change at low accelerations typical of galactic outskirts, potentially eliminating the need for dark matter while explaining observed galactic rotation curves through modified gravitational physics. MOD theory predicts that galaxies with low surface mass densities should exhibit gravitational behavior consistent with ordinary matter alone, exactly matching observations of dark matter-free galaxies. Under MOD dynamics, NGC 1052-DF2 and similar systems represent natural outcomes of galaxy formation, rather than exceptional cases requiring exotic formation mechanisms. Dr. Stacy McGaugh from Case Western Reserve University argues that dark matter-free galaxies provide crucial tests distinguishing between dark matter theories and modified gravity alternatives. If galaxy formation requires dark matter halos, as lambda-CDM models predict, then dark matter-free galaxies must form through exceptional processes. If MOD theory correctly describes gravitational dynamics, then dark matter-free galaxies represent expected outcomes under specific environmental conditions. The formation mystery deepens when considering cosmic environment effects on galaxy formation processes. Both NGC 1052 DF12 and NGC 1052 DF4 exist in the outskirts of galaxy groups dominated by massive elliptical galaxies, suggesting that environmental factors might influence dark matter retention during galactic evolution. Group environments provide complex gravitational fields, hot intragroup gas, and high-velocity encounters that could affect dark matter and ordinary matter differently. NASA's Chandra X-ray Observatory observations reveal hot gas environments surrounding galaxy groups that can interact with dark matter and ordinary matter through different physical mechanisms. Ram pressure stripping, hydrodynamic forces exerted by hot gas on galaxy contents, might preferentially remove diffuse dark matter while preserving denser stellar components. Though current models suggest this mechanism alone cannot account for complete dark matter removal. The Atacama Large Millimeter Array has searched for molecular gas in dark matter-free galaxies to investigate whether unusual gas content or dynamics might indicate exotic formation histories. These observations reveal normal interstellar medium properties without obvious signs of recent gas stripping or heating that might accompany violent dark matter removal processes. Alternative formation scenarios invoke cosmological processes operating during galaxy formation epochs billions of years ago. Dr. Haseo Corby from the Center for Astrophysics and Space Sciences suggests that dark matter-free galaxies might represent fossil remnants of cosmic structure formation when dark matter and ordinary matter were less tightly coupled than in current galactic systems. These cosmological formation models propose that dark matter-free galaxies formed during cosmic epochs when feedback processes from early stellar populations could more easily separate ordinary matter from dark matter halos. As cosmic structure evolved and feedback mechanisms weakened, most galactic systems retained dark matter coupling, but occasional systems might have preserved dark matter-free configurations as cosmological fossils. But cosmological formation models face challenges explaining why dark matter-free galaxies exist preferentially in specific cosmic environments rather than being randomly distributed throughout cosmic structure. If these systems represent cosmological fossils, their environmental clustering suggests formation mechanisms tied to local rather than primordial cosmic processes. Consider the profound implications of formation mysteries surrounding dark matter-free galaxies. These systems challenge our understanding of galaxy formation so fundamentally that explaining their existence requires invoking exotic physics, exceptional cosmic processes, or revolutionary modifications to gravitational theory itself. The formation mechanisms proposed to explain dark matter-free galaxies, tidal stripping, primordial feedback, modified gravity, environmental effects, each reveal new aspects of cosmic structure formation that were apparent from studying ordinary dark matter-dominated galaxies. Understanding how these impossible galaxies formed could revolutionize our comprehension of cosmic evolution across cosmic time. Now, we're going to explore how dark matter-free galaxies are being used as crucial tests of alternative theories of gravity, and why these cosmic laboratories might reveal that our fundamental understanding of gravitational physics requires complete reconstruction. Chapter 4. Testing Gravity. Dark matter-free galaxies have become the ultimate testing ground for one of the most fundamental questions in physics. Is dark matter real? Or have we been misunderstanding gravity itself for over 3 centuries? These cosmic laboratories provide unprecedented opportunities to distinguish between competing theories of gravitational physics, potentially revealing whether the universe operates according to Newtonian dynamics supplemented by exotic dark matter or according to modified gravitational principles that eliminate dark matter's necessity entirely. The testing begins with modified Newtonian dynamics, MOND, developed by Israeli physicist Mordechai Milgram in 1983 as an alternative to dark matter theories. MOND proposes that Newton's second law, F equals ma, breaks down at extremely low accelerations typical of galactic outskirts, where gravitational accelerations become much weaker than anything experienced in terrestrial or solar system environments. Under Mont dynamics, gravitational attraction becomes stronger than Newtonian predictions at low accelerations, naturally producing flat galactic rotation curves without requiring dark matter. Dr. Stacy McGaugh from Case Western Reserve University has spent decades testing Mont predictions against astronomical observations, finding remarkable agreement between Mont theory and galactic dynamics across hundreds of observed systems. Mont successfully predicts rotation curves for spiral galaxies, velocity dispersions in elliptical galaxies, and gravitational lensing effects in galaxy clusters, suggesting that modified gravity might explain cosmic structure without requiring exotic dark matter particles. But Mont theory makes specific predictions about low surface brightness galaxies that provide crucial tests distinguishing between dark matter and modified gravity explanations. Mont predicts that galaxies with extremely low surface mass densities should exhibit gravitational behavior consistent with ordinary matter alone, since low-density systems never reach acceleration thresholds where Mont effects become significant. This prediction matches observations of dark matter-free galaxies almost perfectly. NGC 1052 DFDWO exhibits surface mass density approximately 100 times lower than typical spiral galaxies, placing it precisely in the regime where Mont theory predicts minimal deviation from Newtonian dynamics. Under Mont, this galaxy should behave gravitationally as if it contains only ordinary matter, exactly matching observed globular cluster velocities and stellar dynamics. Dark matter theories, conversely, predict that all galaxies should exhibit substantial dark matter components regardless of surface density. The European Southern Observatory's MUSE spectrograph has enabled precise measurements of stellar kinematics within dark matter-free galaxies, providing detailed tests of gravitational dynamics at low acceleration regimes. These observations reveal stellar velocity dispersions consistent with ordinary matter gravitational influence alone, supporting Mont predictions while challenging dark matter models that require invisible mass components to explain galactic stability. Dr. Federico Lelli from the European Southern Observatory has conducted systematic comparisons between Mont predictions and observed galaxy properties across broad ranges of surface density, stellar mass, and environmental conditions. These studies reveal that Mont theory successfully predicts which galactic systems should exhibit dark matter-like behavior and which should behave according to ordinary matter dynamics alone. But testing gravity through dark matter-free galaxies extends beyond Mont theory to encompass broader classes of modified gravity models. Tensor vector scalar, TeVe's gravity, developed by Dr. Jacob Bekenstein, provides relativistic extensions of Mont dynamics that remain consistent with general relativity as successes, while modifying gravitational behavior at cosmic scales. TeVe's theory makes specific predictions about gravitational lensing, cosmic structure formation, and galaxy dynamics that can be tested through observations of dark matter-free systems. Emergent gravity theories, proposed by Dr. Erik Varleen from the University of Amsterdam, suggest that gravitational attraction emerges from quantum entanglement effects operating on cosmic scales. These theories predict that gravity behaves differently in high-entropy environments typical of galactic outskirts, potentially explaining flat rotation curves and dark matter-free galaxies through quantum mechanical processes rather than exotic matter components. The testing becomes more sophisticated when considering gravitational lensing effects around dark matter-free galaxies. If these systems truly lack dark matter, they should produce gravitational lensing consistent with their visible stellar masses alone. The Hubble Space Telescope's Advanced Camera for Surveys has begun searching for weak lensing signals around ultra-diffuse galaxies to test whether their gravitational effects match visible matter estimates or require additional invisible mass components. Dr. Massimo Meneghetti from the Observatory of Bologna has developed techniques for measuring gravitational lensing in low-mass galactic systems using combined observations from multiple space telescopes. These measurements provide direct tests of gravitational field strength around dark matter-free galaxies, potentially distinguishing between dark matter theories that predict invisible mass components and modified gravity theories that predict gravitational enhancement through dynamical mechanisms. But gravity testing through dark matter-free galaxies faces significant observational challenges due to the faint surface brightness and low mass of these systems. Measuring precise stellar kinematics requires lengthy observations with the largest ground-based telescopes, while detecting gravitational lensing effects demands exceptional image quality and careful control of systematic errors that could mimic or mask genuine gravitational signals. The Atacama Large Millimeter Array provides complementary tests through molecular gas kinematics in dark matter-free galaxies. Gas dynamics offer independent probes of gravitational fields that aren't affected by stellar population uncertainties or dynamical heating mechanisms that could complicate stellar kinematic measurements. If dark matter-free galaxies truly lack invisible mass components, their gas dynamics should match gravitational models based on stellar masses alone. NASA's Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct comprehensive weak lensing surveys capable of detecting gravitational effects around thousands of ultra-diffuse galaxies. These surveys will provide statistical tests of modified gravity theories by measuring whether low-surface density galaxies systematically exhibit gravitational behavior consistent with dark matter theories or modified gravity predictions. The testing reveals profound implications, regardless of which theoretical framework proves correct. If dark matter theories successfully explain dark matter-free galaxies through exotic formation mechanisms, then dark matter's fundamental role in cosmic structure receives additional confirmation, while revealing previously unknown aspects of galaxy formation and evolution processes. If modified gravity theories better explain observations of dark matter-free galaxies, then our understanding of gravitational physics requires revolutionary reconstruction with implications extending far beyond cosmology to encompass fundamental physics, planetary dynamics, and gravitational wave astronomy. Modified gravity would represent the most significant revision to physical law since Einstein's general relativity. Consider the remarkable fact that cosmic structures located tens of millions of light years from Earth are providing crucial tests of gravitational physics that cannot be replicated in any terrestrial laboratory. The weak gravitational fields and low acceleration regimes characterizing galactic dynamics exceed anything achievable through human technology, making astronomical observations essential for testing fundamental physical theories. Your understanding of gravity itself depends on resolving whether dark matter-free galaxies represent exotic cosmic accidents within dark matter-dominated cosmic structure or natural outcomes of modified gravitational dynamics operating throughout cosmic space. The resolution could transform physics from elementary particle research to cosmic structure formation across every scale of physical reality. Dark matter-free galaxies demonstrate how astronomical discoveries can challenge fundamental physical principles that have guided scientific research for centuries. These cosmic laboratories provide unique opportunities to distinguish between competing theories of gravity and matter that make identical predictions for most observable phenomena, but differ dramatically in their implications for cosmic structure and fundamental physics. Now we're going to explore how environmental factors surrounding dark matter-free galaxies might influence their formation and evolution, and why understanding cosmic environment effects could reveal new mechanisms for creating and maintaining galactic structure without dark matter scaffolding. Chapter 5. Environmental influence. The Cosmic neighborhoods surrounding dark matter-free galaxies hold crucial clues to understanding how these impossible systems formed and continue existing in apparent violation of standard cosmological models. Both NGC 1052 DF2 and NGC 1052 DF4 reside in the outskirts of galaxy groups, dominated by massive elliptical galaxies, suggesting that specific environmental conditions might enable galaxy formation without dark matter halos or facilitate dark matter removal through environmental processes. The environmental story begins with recognizing that galaxies do not evolve in isolation, but within complex cosmic ecosystems that include neighboring galaxies' hot, intergroup gas gravitational tidal fields and high-velocity encounters that can dramatically alter galactic structure over cosmic time. Dr. Annalisa Pulapich from the Max Planck Institute for Astronomy has conducted comprehensive simulations revealing how environmental factors influence galaxy formation and evolution through mechanisms that affect dark matter and ordinary matter differently. NGC 1052, the massive elliptical galaxy dominating the local group environment, contains approximately 200 billion solar masses and generates gravitational fields extending millions of light years beyond its stellar boundary. This gravitational influence creates complex tidal effects that could strip dark matter from smaller galaxies while leaving stellar components intact, potentially explaining why dark matter-free galaxies exist preferentially in group environments, rather than being randomly distributed throughout cosmic space. Dr. Duncan Forbes from Swinburne University has analyzed the spatial distribution of ultra-diffuse galaxies around massive central galaxies, finding that systems with anomalously low dark matter content cluster preferentially at specific distances from group centers. This clustering suggests environmental processes operating most efficiently at intermediate distances, where tidal forces are strong enough to affect dark matter halos, but not so strong as to completely disrupt stellar populations. But environmental influence extends beyond gravitational effects to encompass hydrodynamic processes involving hot intergroup gas that fills space between galaxies within group environments. The Chandra X-ray Observatory has revealed that galaxy groups contain hot gas with temperatures exceeding 10 million Kelvin, creating environments where ram pressure stripping could remove both dark matter and ordinary matter from galaxies moving through the intragroup medium. Ram pressure stripping occurs when galaxies move through hot gas environments at high velocities, creating hydrodynamic forces that can strip loosely bound material from galactic systems. Dr. Bianca Poggianti from the Observatory of Padova has studied ram pressure effects in galaxy clusters, revealing how high-velocity encounters with hot gas can remove both interstellar gas and potentially dark matter from galaxies over timescales of hundreds of millions of years. The effectiveness of ram pressure stripping depends critically on galaxy velocity, gas density, and the binding energy of different galactic components. Dark matter being distributed in extended halos with lower binding energy than central stellar regions could be preferentially removed through ram pressure mechanisms while stellar cores remain gravitationally bound within stripped galactic remnants. But ram pressure models face challenges explaining complete dark matter removal while preserving substantial stellar populations observed in dark matter-free galaxies. Computer simulations by Dr. Yannick Bai from Leiden University show that ram pressure stripping typically removes dark matter and interstellar gas simultaneously, making it difficult to produce galaxies with normal stellar content, but no dark matter component through purely hydrodynamic processes. Environmental influence also operates through galaxy-galaxy interactions that become more frequent and intense within group environments. Close encounters between galaxies can trigger tidal stripping, stellar heating, and orbital evolution that affects dark matter and stellar components differently depending on their spatial distribution and binding energies within galactic gravitational potentials. Dr. Vicente Rodriguez Gomez from the University of Guanajuato has simulated galaxy interactions within group environments, revealing complex scenarios where repeated encounters can gradually strip dark matter halos while stellar populations remain bound through higher central concentrations. These interaction models predict that dark matter-free galaxies should exhibit stellar kinematics indicating recent dynamical heating consistent with environmental processing. The Very Large Array Radio Telescope has searched for neutral hydrogen gas in dark matter-free galaxies to investigate environmental effects on galactic gas content. If environmental processes remove dark matter through hydrodynamic mechanisms, they should also affect interstellar gas distribution and kinematics in ways that provide observational signatures of environmental influence on galactic evolution. Environmental influence might also operate through mechanisms involving feedback from central supermassive black holes in massive group galaxies. Active galactic nuclei can inject enormous amounts of energy into surrounding environments, eating intergroup gas and creating outflows that could affect dark matter distribution within satellite galaxies orbiting at group peripheries. Dr. Melanie Habuzit from the Max Planck Institute for Astronomy has studied feedback effects from supermassive black holes on cosmic structure formation, revealing how active galactic nuclei can influence galaxy formation across distances exceeding millions of light-years. These feedback mechanisms could preferentially affect dark matter in low-mass satellite galaxies while preserving stellar populations that formed before feedback became dominant. But environmental influence models must explain why dark matter-free galaxies remain rare, even within group environments where proposed mechanisms should operate frequently. If tidal stripping, ram pressure effects, or feedback mechanisms readily produce dark matter-free systems, then group environments should contain many more such objects than currently observed through systematic surveys. The Dragonfly telephoto array continues discovering ultra-diffuse galaxies in various environmental contexts to determine whether dark matter-free systems exist exclusively in group environments or represent more general galactic populations that happen to be most easily detected in specific cosmic neighborhoods. These surveys will reveal whether environmental processing is necessary for dark matter-free galaxy formation or merely influences their detectability. Environmental influence studies also investigate whether dark matter-free galaxies exhibit observational signatures consistent with environmental processing scenarios. If these systems form through tidal stripping or ram pressure effects, they should display stellar streams, asymmetric morphologies, or kinematic disturbances indicating recent dynamical disruption. Current observations reveal remarkably regular stellar distributions without obvious signs of recent environmental processing. The European Space Agency's Euclid mission will conduct comprehensive surveys of galaxy groups and clusters to identify environmental factors that correlate with ultra-diffuse galaxy properties and dark matter content. These observations will test whether specific environmental conditions systematically produce galaxies with reduced dark matter content, or whether dark matter-free systems represent intrinsic galactic properties unrelated to environmental processing. Consider the philosophical implications of environmental influence on fundamental galactic properties like dark matter content. If cosmic environment can determine whether galaxies contain dark matter halos, then dark matter's role in cosmic structure might be far more conditional and contextual than current theories suggest. Dark matter could represent a default galactic component that environmental processes can remove, rather than a fundamental requirement for galaxy formation. Environmental influence studies reveal that cosmic context might be as important as intrinsic physical processes for determining galactic properties and evolution trajectories. Your understanding of galaxy formation must incorporate environmental factors operating across scales from local galaxy interactions to cosmic structure evolution across billions of years of cosmic time. The environmental neighborhoods surrounding dark matter-free galaxies provide natural laboratories for testing How cosmic context influences fundamental aspects of galactic structure and evolution. These cosmic ecosystems might reveal that galaxy formation operates according to environmental principles that make dark, matter-free systems natural outcomes under specific cosmic conditions rather than exotic violations of cosmic law. Now we were going to explore alternative theories of cosmic structure that attempt to explain dark, matter-free galaxies without invoking exotic formation mechanisms, and why these theoretical frameworks could revolutionize our understanding of cosmic evolution and fundamental physics.